Welcome back. So, today we will begin the study of probability theory from the basic axiomatic perspective. So, we will start building on the basic probability axioms and work towards defining probability spaces, probability measures and so on. Okay. So, in this mathematical theory of probability, so it is an axiomatic theory which starts off assuming that there are two entities which are not defined. Okay. So, the two entities which are not defined in the beginning are the following. So, the first is the concept of a random experiment. Okay. So, this is we do not define what it is. Okay. So, just like so we have to be and we have to understand it like just in English, right. It is an experiment whose outcome is random, all right. So, which brings me to the second undefined concept, which is outcome of the random experiment. Okay. So, these two concepts are not defined. Okay. So, you cannot make a so just like in geometry you do not define a point, right, or number theory you do not try to define what a number is, right. So, you have to start off somewhere, you can only define certain things in terms of certain other things you understand, you cannot define everything, right. So, probability begins with two entities which you do not question or try to define. Okay. So, there is a random experiment. So, it is an experiment whose outcome is random just as the English says, and it has an outcome, right. Every time you perform this random experiment there is an outcome, right. So, and that is it, right. You cannot say anything more about these terminologies, that is all there is to it. Now, everything in probability that is defined is defined in terms of these entities, okay, and then we build up from here on. Okay. So, the first most important concept, most basic concept that is defined is the concept of a sample space. Okay. The sample space of a random experiment. So, it is often denoted by the capital Greek letter omega, okay, big omega. Okay. So, it is defined as the set of all possible outcomes of the random experiment. Okay. Okay. So, if you see this is a definition of a sample space. So, I have defined a sample space in terms of these two things I have not defined, right. So, I have defined it in terms of two things which I have not defined, that is the way it always progresses, right. So, you think you understand these two things and you move on and define other things in terms of things you did not divide in the first place, right, that is how it works. So, this is a sample space, okay. It is just a set, the set containing all possible outcomes of a random experiment. So, whatever outcome is possible, everything should be included, it should not leave behind any possible outcome, right. Now, so you can, so for example, you can always say, so to give an example, so let us say toss a coin once. Okay. So, here you want to know what the sample space is. Okay. So, now the thing I want to emphasize here is what a sample space is corresponding to a random experiment itself depends on what you are interested in. Okay. So, it is not, so if it so happens that I am tossing a coin, that is my random experiment, and if I want to know what the face it lands on, okay, then the sample space will have two elements in it, right, heads and tails, assuming that it does not land vertically, it will have only two outcomes, right, two heads and tails. However, it is not true that the random experiment of tossing a coin once always have to have this sample space. It depends on what you are interested in. Somebody else may be interested in finding out how many times the coin tumbles in the air, right. In that case your sample space is not head tail, right. In that case your sample space will be the number of times, the all possible number of times it tumbles. So, which is probably positive integers, right. Yes.
Shouldn't the definition then be all possible interested outcomes?
Yeah. So, which is why the outcome itself depends on what the experiment is interested in, right. So, I may toss a coin, but you may be interested in counting the number of tumbles and somebody else may be interested in the phase it lands in, right. So, it is not so the what is an outcome itself depends on what you are interested in, which is why the sample space depends on what you are interested in, right. So, this is something I want to emphasize. So, if you are, so this is the experiment, okay. So, so this is what tossing a coin once. So, if we are interested the phase that shows up, the phase that shows, then your omega will be simply head then tails. It will only have two elements, right. There are only two possible outcomes. But for the same random experiment, so if you are interested in the number of tumbles say, right. So, in this case it is reasonable to say that your omega will be some subset of natural numbers or the natural numbers themselves, right. If any number of tumbles are possible, then you would want to choose omega equal to n, right. So, it is not, so even for a given random experiment it is not as though what is an outcome or what is the set of all possible outcomes is very much a function of what you are interested in looking at, right. So, it depends on what you are interested in studying or modeling, right. So, this is something I want to, this is a conceptual point. So, I just want to make this very clear. So, you may be interested in the velocity with which the coin strikes the ground, right. It seems a bit strange, you may be interested in knowing that, right. So, in this case probably you should choose r plus or some subset of r plus, right, some positive real numbers, right. So, you understand what I am trying to say here. So, the sample space capital omega depends on not only on the random experiment, but what you are interested in measuring or knowing, right. And as you can see, just here we have seen that the omega could be finite samples, there is a set of all possible outcomes could be finite or infinite. Actually, here it is countably infinite, here it is uncountably infinite, right. So, there are all these possibilities exist. You could have an omega which is finite, you could have an omega which is countably infinite, you could have an omega which is uncountable, right. All this is possible depending on what you are interested in looking at. Right. And so an elementary outcome, so an outcome of the random experiment. So, let us say you have fixed what you are interested in, okay. You let us say you are interested in the number of tumbles or whatever, right. Then, so an outcome is sometimes known as an elementary outcome, okay. So, this is also a terminology, outcome and elementary outcome are one and the same, right. So, an outcome or elementary outcome is denoted by little omega, all right. This is the little, this is not a w, this is a the Greek letter little omega, and this is an element of your sample space omega and big omega. Okay. So, now here is, so this little omega, right, the choosing of the little omega is what is random, all right. This is the thing that you have no control over. Okay. In probability theory, this is in fact the source of randomness, right. So, you have a sample space, you have built a sample space of the set of all possible outcomes depending on what you are interested in, and then this little omega is chosen by some, you can think of it as a genie or some goddess of chance who picks it, right. You have no control over it, and every time you run a random experiment, the goddess of chance picks a little omega from this big omega, okay, and that you do not question. Okay. You have no way of controlling that. Okay. You can think of it as the weather tomorrow, which is like a natural phenomenon or something else, right, something that you have no control over, right, or full knowledge of or ability to model or something like that. So, this is where the randomness is. Okay. So, the selection of the, so you have big sample space, this is a set of all possible outcomes, and which particular omega realizes when you run the experiment once is in fact the source of randomness. You can think of it as being picked by a genie, okay, and every time you run the experiment, it will be a different little omega picked from the sample space, okay, and this is the source of randomness in probability theory. Okay, this is the thing that you do not have control. This is okay. Any questions on this?
So, outcome is a single outcome or is a subset?
Yeah. So, it is an elementary. So, an elementary outcome, which is why it is called an elementary outcome. So, outcome is a particular point in omega. So, if you can, so in this particular case, if your omega is this h and t, there are only two possible elementary outcomes. So, little omega must be either h or t, it could be different at different runs of the random experiment, but it is a singleton. Okay, it is just a one element of capital omega.
Can omega be combination of tumbles and phases also?
Yeah, so if you are interested in, so yeah, it really depends on what you are interested in, right. If you want to measure both, you will have an omega, big omega correspondingly, right.
Because the sample set may contain natural numbers and some HT.
No, that is fine. Yeah, so it is, see, you have to decide what you are interested in, right. You have to build the sample space after all. So, there is some random experiment going on, either you are running it or nature is running it, but what you consider the sample space is obviously a function of what you are interested in determining, right. You may be interested in determining the velocity or number of tumbles or whatever it is that you want to, this thing, you put that in the sample space, but it should contain all possible elementary outcomes, should not leave out any possible outcome, that is all, right. So, you have to determine that. So, in everything I am going to, so in building a probability space, we have to, it is our responsibility to determine what the sample space is and so on, right. We will see that it is our responsibility to determine what the probability should be also. Okay. Is it okay? Everybody okay? So, for another example, let us say toss a coin n times and you are interested in determining the phases that show. Okay. So, now you are tossing a coin n times, the same coin you are tossing n times, okay, and you are interested in the phases that show. Okay. So, now you can look at this experiment as n different repeats of this experiment, or you can just say this whole n trials is one random experiment. That is also a valid way of looking at it, right. You toss a coin n times or toss all n coins all at once, right, and say that string of n outcomes that I see, n faces that I see, that is really what I am interested in, that is the elementary outcome I am interested in. So, in that case, so your omega will be all possible heads and tails, all 2 power n possibilities of heads and tails, right. So, it should be h t power n, right. So, each elementary outcome, each little omega in this sample space will be like h t t h h h t t, some n string of heads and tails, and this each of these elementary strings of h t t h is considered an elementary outcome if you just say that all n tosses corresponds to the random experiment, right. That is also a valid way of looking at it. Okay. So, this is what kind of a sample space is this? It is a finite sample space, there are only 2 power n elements, right. N is fixed, n may be 10 or 20 or whatever, but there will be only 2 power n possible elements in the sample space corresponding to the 2 power n possible strings of heads and tails, right. Now, you can also, now this is let us say 1, toss a coin infinitely many times. And then again you are interested in the all the faces that show. Okay. So, now you may get you may well you may wonder how do I toss a coin infinitely many times, will I ever finish and so on, right, and then will I ever finish recording my outcomes and so on. But these things you do not worry about in probability theory. Okay. Again you will just say that you are tossing some coin infinitely many times. So, your omega, the set of all possible outcomes, is what? The set of all possible strings of heads and tails, infinite strings of heads and tails, right. So, every trial of the random experiment. So, I want to emphasize here that one trial of the random experiment is not tossing a coin once, right. One trial is a particular infinite string of heads and tails. Okay. So, in this particular case your so this is the infinite strings of heads and tails, and your omega for example may be the string h h t h t t h something, right, some string of infinite string of heads and tails. Okay. This is an elementary outcome, it is not like that is an elementary outcome. Okay. So, now your random experiment itself is tossing it infinitely many times, and you do not ask questions like, oh, will I ever finish, will I ever be able to count, right, you do not ask that, right. That is the experiment and that is your sample space. Okay. And what kind of a sample space is that? It is an uncountable sample space, because it is like you can say h is 0, t is 1. So, it is like 0 1 power infinity. So, now you are all very familiar with Cantor's argument. So, this guy is an uncountable sample space, right. So, there are many examples you can give, right. You can take a line, you are throwing darts at the line, and the let us say it is the 0 1 interval, you are throwing darts at the 0 1 interval, and the elementary outcome will be some real number between 0 and 1, and the sample space will be in fact that interval itself, another uncountable sample space, right. So, these are some examples.
Actually, in the third case, if you are interested in the velocity with the coin strikes, so in that case our sample space is the set of real numbers.
Well, the positive real numbers.
No, actually, it's basically a continuous set. Actually, continuous.
It's an uncountable set.
No, actually, I'm saying it's a continuum of values. Continuous values we are counting like.
Yes. Okay.
So, if you are interested in a particular velocity, then the probability that we assume will be 0 always, because we are taking.
I have not said that, right. So, that is something. Yeah. So, that is you are getting ahead of me by several lectures, right. I am only talking about the sample space now, right. What are the set of all possible outcomes? I have not said anything about probability so far, have I? Right. Okay. So, sample space, okay, everybody okay with sample space? Okay. So, now So, in probability, right. So, we are often interested not in whether a particular elementary outcome has occurred or not, we are often interested in whether a subset of a sample space has occurred or not. Okay. So, we may be interested, let us say if we toss a coin n times, we may not actually say, oh, what is the specific string that came up, we may say, oh, is the number of heads even, right. So, those are things that are of actually modeling interest, so to speak, right. So, you may be interested in whether this is your sample space, you may not really care whether this elementary outcome showed up or some other elementary outcome showed up, but you may say, oh, did that subset show up, right. Right. So, and so in the case of this number of tuples, you can say, oh, there is the number of tuples greater than 5, right. So, it is not an elementary outcome in the sense, right. So, these kind of subsets of sample space which are of interest to the modeler, interest to the person doing this business of probability modeling. So, these subsets are called events. Okay. So, this is I just gave a very informal definition, okay, because the formal definition requires more build up. Okay. So, maybe I wonder if I should just write this definition down. So, let us say informally subsets of a subset, should we say informally let me just say subsets of omega which are of interest are called events. So, I may be, so for example, on the toss a coin thrice and you are interested in the faces. So, your sample space is h t power 3, you may be interested in, so the event of interest may be this at least 2 heads. Okay. So, in this case you are not really asking, so I toss the coin 3 times, I am not really asking if whether a particular string showed up, I am asking if at least 2 heads showed up, right. So, this corresponds to more than one elementary outcome, right. So, in particular, so what are the outcomes that correspond to this? So, you have let us say first of all you can have all heads, right, or you can have T H H, right, H T H, H H T, is there anything else? That is it, right. So, these are the elementary outcomes. When you toss a coin thrice, the elementary outcome is a string of 3 string of heads and tails, and the event of interest. So, you are asking me the question, oh, did at least 2 heads showed up, that corresponds to these strings, which is actually a subset of that of the sample space. Okay. So, for all for all colloquial purposes an event is a subset of the sample space, okay, except that is not the entire story. Okay, that is something we will get to later. Okay, for now you can just consider an event as a subset of the sample space, okay, but I have put something into quotes here, they are of interest to us, right. So, we will see later that all events are in fact subsets of the sample space, events are necessarily subsets of the sample space, but just put a caveat in your mind that not all subsets of the sample space are necessarily considered events. Okay. Only those subsets which are of interest, which we are interested in assigning probabilities to in particular, are called events. Okay. So, all events are subsets of omega, right. So, you can call this event A for example, right. This is this event is a subset of omega, right. So, all events are subsets of omega, but not all subsets of omega are necessarily considered events, okay. And this is not a point that you will completely appreciate now. Okay. So, if you are a little bit confused, okay, we will get to it, right. So, this is something just bear in mind, okay. Not all subsets of omega are considered events, okay. Everybody fine?